You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. At the heart of artificial intelligence lies the ability to solve problems. Problem solving is the essence of intelligence, whether it takes the form of humans planning a route across town or machines finding optimal solutions in complex systems. In AI, many challenges, planning, reasoning, decision-making are framed as problems requiring systematic solutions. A problem is defined by its starting conditions, possible actions, and goals. Once represented this way, algorithms can be designed to search through possible solutions. Unlike human intuition, which often leaps to answers, machines rely on structured exploration, ensuring that solutions are not only found, but also evaluated for efficiency. By viewing intelligence as problem-solving, AI provides a unifying lens through which tasks as diverse as playing chess, diagnosing illness, or navigating a robot through a maze can all be understood as variations of the same fundamental process. Search is the mechanism by which AI systems explore possibilities in pursuit of solutions. Imagine standing in a maze and deciding which paths to try. Each choice leads to new possibilities, and exploring these systematically is the essence of search. In AI, search algorithms act like explorers, examining different sequences of actions to discover paths from a starting state to a goal state. Some approaches examine every possible option, while others employ shortcuts or heuristics to focus on promising areas. This systematic exploration allows machines to solve puzzles, plan tasks, and optimize outcomes in a way that mirrors human problem-solving strategies but operates with mechanical precision. Search illustrates that intelligence, at least in part, is about navigating choices effectively. Central to this idea is the concept of a state space. A state represents a snapshot of the problem at a given point in time, while transitions describe the actions that move from one state to another. Collectively, the state space forms a map of all possible configurations of the problem. For instance, in solving a Rubik's Cube, each arrangement of the cube is a state, and each twist is a transition. The AI system's task is to find a sequence of transitions that leads from the starting state to the goal state. This framing provides a structured way to model problems, whether they involve puzzles, logistics, or strategic games. By defining state spaces, AI transforms abstract challenges into navigable landscapes of possibilities. Uninformed search strategies, also called blind search methods, are approaches that explore state spaces without relying on domain-specific knowledge. These algorithms systematically examine possibilities, ensuring completeness but not efficiency. The advantage is their generality. They can be applied to any problem that can be framed as a state space. However, their lack of guidance often makes them slow or impractical for large problems. They're like someone searching for a lost key by checking every possible spot in a house one by one, without considering where the key is most likely to be. Despite their simplicity, uninformed strategies lay the groundwork for more advanced methods by establishing the principles of systematic exploration. Breadth-first search is a classic uninformed strategy that explores level by level. Starting from the initial state, it examines all possible moves before proceeding to the next depth of exploration. This method guarantees finding the shortest path in terms of steps, making it useful for problems where path length matters. For example, if you want the minimum number of moves to solve a puzzle, breadth-first search ensures the solution is optimal in that sense. The downside is memory usage. It must store all explored states at each level, which quickly becomes impractical in large search spaces. Still, breadth-first search illustrates the rigor of systematic exploration and provides a foundation for understanding more sophisticated strategies. Depth-first search takes a different approach, exploring one branch of the state space deeply before backtracking. It follows a path as far as possible, and if it reaches a dead end, it retraces its steps to try alternatives. This method requires less memory than breadth-first search because it only needs to track the current path. However, it does not guarantee the shortest solution, and it risks getting stuck in deep, unpromising paths. An analogy is searching for a friend in a building by walking down one hallway entirely before trying another, without considering efficiency. Depth-first search is efficient in terms of storage but can be wasteful in effort, highlighting the trade-offs that characterize search strategies. Uniform cost search introduces the idea of evaluating paths based on cost rather than number of steps. Instead of assuming all moves are equal, this method considers that some actions may be more expensive than others. For example, in navigation, one path might be longer but smoother, while another is shorter but more difficult. Uniform cost search always expands the least costly path so far, guaranteeing an optimal solution in terms of total cost. This strategy demonstrates how adding information about the problem can improve outcomes, shifting the focus from simply finding a solution to finding the best one according to defined metrics. Informed search strategies take this idea further by incorporating heuristics estimates of how promising a given path might be. Unlike uninformed methods that blindly explore, informed searches use domain-specific knowledge to guide exploration, often dramatically improving efficiency. A heuristic might estimate the distance remaining in a navigation problem or the number of misplaced tiles in a puzzle. These estimates do not guarantee accuracy but provide valuable direction. Informed strategies reflect a balance between rigor and intuition, much like human reasoning, which often relies on educated guesses rather than exhaustive checks. They illustrate how incorporating even rough guidance can transform search from impractical to powerful. Heuristics in AI function as rules of thumb for estimating costs or values in search. A good heuristic is both admissible, never overestimating the true cost, and consistent, meaning it maintains logical order across states. For example, in navigating a map, straight-line distance between cities is often used as a heuristic for driving distance. It may not be exact but provides a reasonable guide. Effective heuristics can drastically reduce the number of states explored, making problems solvable that would otherwise be intractable. However, poorly designed heuristics can mislead search, wasting effort. This highlights the art of heuristic design, balancing simplicity, accuracy, and computational feasibility to support effective problem-solving. Best first search is an informed strategy that always expands the most promising state according to its heuristic estimate. It essentially asks, which option looks best right now, and pursues that path first. This method can be highly efficient in many contexts, particularly when heuristics are well designed. However, it may get trapped in suboptimal paths if the heuristic is misleading. Best first search mirrors human intuition, where we often choose the option that seems most appealing immediately, even if it is not the ultimate best. In AI, its value lies in providing a practical compromise, faster than exhaustive methods, though not always guaranteed to find the optimal solution. The A-star algorithm refines best first search by combining path cost with heuristic estimates. It evaluates paths not only on how promising they look, but also on how much has already been invested in reaching them. This balance of cost so far and estimated cost to the goal makes A-star one of the most widely used and effective search algorithms in AI. It guarantees finding an optimal solution as long as the heuristic is admissible, while often exploring far fewer states than uninformed methods. Applications range from route planning in GPS systems to solving puzzles like the sliding tile problem. S-star exemplifies the marriage of mathematical rigor and heuristic intuition, embodying the strengths of informed search. Local search methods approach problem-solving differently, focusing on incremental improvements rather than exhaustive exploration. Hill climbing is a classic example, where the algorithm evaluates neighboring states and moves toward whichever seems better. This approach is useful when the full state space is too vast to map, but it risks becoming stuck in local optima solutions that are better than their immediate neighbors but not the global best. Local search methods illustrate the pragmatic side of AI problem-solving, Sometimes, good enough is sufficient, and exploring incrementally can produce practical solutions quickly, even if they are not guaranteed to be perfect. Constraint satisfaction problems provide another lens for search, framing challenges as sets of variables that must satisfy specific conditions. Examples include scheduling tasks, assigning colors to maps so no neighbors share a color, or solving Sudoku puzzles. The goal is not to minimize cost or path length, but to find any arrangement that meets all constraints. AI systems solve these by systematically assigning values to variables while checking conditions, often using heuristics to guide choices efficiently. Constraint satisfaction highlights the diversity of search applications, showing that problem-solving is not only about paths and costs, but also about satisfying logical requirements within defined boundaries. Game playing illustrates one of the most engaging applications of search in AI. Games like chess, checkers, or Go can be framed as search problems, where each move creates a new state and players explore possibilities to achieve victory. AI systems simulate future moves, evaluate outcomes, and select strategies accordingly. Game playing has historically been a showcase for AI, with milestones like Deep Blue's victory over Garry Kasparov in chess demonstrating the power of search-based problem-solving. These successes highlight the ability of machines to navigate vast, branching possibilities and make decisions that rival human expertise, especially in well-defined domains. Despite their strengths, search approaches face significant limitations, particularly in scalability. Many real-world problems involve search spaces so vast that exploring every possibility is impossible. The branching factor, the number of choices at each step, grows exponentially, quickly overwhelming even the fastest computers. This challenge is sometimes called the combinatorial explosion. For example, while chess has been mastered through search and heuristics, more complex real-world tasks may defy exhaustive exploration. These limits remind us that search, while foundational, cannot solve every problem directly. They also underscore why AI has evolved toward machine learning, heuristics, and hybrid approaches to extend beyond the bounds of pure search methods. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Optimization is a central goal of many search methods in AI. Finding a solution is often not enough. The aim is to discover the best possible solution according to defined criteria. For example, when planning delivery routes, the challenge is not merely to find a path from start to finish, but to minimize distance, time, or fuel consumption. Optimization algorithms evaluate multiple possibilities to identify the most efficient or cost-effective choice. This focus reflects a practical reality. In the real world, resources are limited, and the quality of solutions matters. AI's strength lies not only in solving problems but in optimizing them, making outcomes more effective and valuable. Adversarial search introduces the complexity of competition, where outcomes depend not just on one's own actions, but also on the moves of an opponent. This is the case in two-player games like chess or Go, where each player seeks to maximize their chances of winning while minimizing the others. AI algorithms for adversarial environments must anticipate and counter an opponent's strategies, adding layers of complexity. Unlike single-agent search, where the problem is static, adversarial search must account for dynamic, hostile forces actively working against success. This makes it an important study area not only for games but also for real-world scenarios like cybersecurity, where defenders and attackers constantly adapt to each other's moves. The Minimax algorithm is one of the foundational approaches in adversarial search. It assumes that the opponent will always play optimally, and it evaluates moves by minimizing the possible maximum loss. In other words, the algorithm chooses the path that offers the best worst-case outcome. This cautious strategy ensures resilience against skilled opponents, making it a staple of AI game playing. For example, in chess, Minimax evaluates possible future moves for both sides and selects the one that preserves the strongest position under the assumption of perfect counterplay. While powerful, Minimax can be computationally expensive, as it requires exploring many possible moves and countermoves. Still, it represents a logical way to simulate foresight in competitive settings. Alpha-beta pruning enhances Minimax by cutting away branches of the search tree that are irrelevant to the final decision. If a path is found to be inferior compared to an already explored option, the algorithm can stop exploring it, saving time without sacrificing optimality. This pruning makes adversarial search vastly more efficient, allowing deeper exploration within the same computational limits. In chess programs, for instance, alpha-beta pruning enables consideration of far more moves within practical time constraints. The technique demonstrates a broader principle in AI. Efficiency often comes from eliminating unpromising options rather than exhaustively exploring everything. It shows how smart search can combine rigor with pragmatism to tackle otherwise intractable problems. Stochastic search methods introduce randomness into problem solving, allowing exploration of solutions in a probabilistic rather than deterministic way. Simulated annealing, for example, mimics the cooling of metals, allowing occasional bad moves to escape local optima and eventually converge on a good solution. Genetic algorithms take inspiration from evolution, using mutation and recombination to generate and refine solutions over successive generations. These methods highlight how randomness, far from being a flaw, can be a powerful tool in navigating complex search spaces. They show that sometimes the best path to solving a problem is not rigid logic alone, but a balance of structure and exploration. Evolutionary algorithms exemplify biologically inspired problem-solving. These approaches maintain populations of candidate solutions, evaluate their fitness, and evolve better solutions over time through selection, crossover, and mutation. Applications range from optimizing engineering designs to evolving neural networks. By mimicking natural selection, evolutionary algorithms discover solutions that may not emerge through traditional search. They are particularly useful in problems where the search space is too vast or poorly understood for deterministic methods. These algorithms demonstrate how AI can draw inspiration from the natural world, blending computation with biology to solve challenges that resist direct approaches. Planning in AI extends problem-solving from isolated decisions to sequences of actions aimed at long-term goals. Unlike search, which often focuses on immediate paths, planning considers how individual steps fit into broader objectives. For example, a household robot tasked with preparing dinner must plan not only how to fetch ingredients, but also how to sequence tasks like chopping, cooking, and serving. Planning requires models of actions, outcomes, and constraints, enabling AI systems to chart coherent strategies. This capability moves machines closer to human-like foresight, where present decisions are evaluated in terms of their contribution to future goals. Classical planning methods in AI rely on logic-based frameworks to represent actions and states. Systems like STRIPS, Stanford Research Institute Problem Solver, use formal rules to model how actions transform states, enabling systematic construction of plans. These approaches excel in structured domains where rules are clear and outcomes predictable. However, they often falter in real-world environments that are uncertain or dynamic. Still, classical planning remains foundational, influencing modern techniques and demonstrating the value of structured reasoning in guiding long-term problem-solving. For learners, it provides a clear example of how AI systems can move from isolated problem-solving to coherent strategies. Heuristic planning builds on these foundations by incorporating domain knowledge to guide plan construction more efficiently. Instead of exhaustively exploring every possible sequence of actions, heuristic planning uses estimates to prioritize promising paths. For example, in robotic navigation, heuristics may emphasize shorter routes or safer paths when constructing a plan. This approach allows systems to generate workable strategies more quickly, even in large or complex domains. Heuristic planning reflects the practical reality that optimal solutions are not always feasible to compute, but good solutions delivered quickly can be highly valuable. It blends systematic reasoning with informed shortcuts, much like human planning in daily life. Multi-agent problem-solving extends planning and search into scenarios where multiple AI systems interact. These agents may cooperate, coordinate, or compete, depending on their objectives. For instance, autonomous vehicles must coordinate to avoid collisions, while virtual assistants might share information to fulfill a user's request. Multi-agent systems add layers of complexity because each agent's actions influence others. This dynamic resembles human social systems where collaboration and competition intermingle. For learners, multi-agent problem-solving illustrates how AI expands beyond single machine reasoning into collective intelligence, offering insight into both opportunities and challenges of shared environments. Real-time problem-solving addresses the challenge of making decisions under time constraints. In many applications, autonomous driving, stock trading, or emergency response waiting for an exhaustive search is impractical. Real-time methods prioritize speed, often settling for approximate or good enough solutions within strict deadlines. This approach reflects the real-world principle that timely action can be more valuable than perfect action. For AI, real-time problem-solving demands algorithms that balance accuracy with speed, ensuring that systems can act effectively in dynamic and unpredictable environments. It highlights how problem-solving in AI adapts to the demands of practical deployment. Approximation and satisficing are strategies that acknowledge the impracticality of always finding optimal solutions. In many real-world problems, the cost of perfection outweighs its benefits. AI systems often aim for solutions that are good enough, balancing quality with efficiency. For example, a scheduling system might not find the absolute best timetable, but instead deliver one that meets constraints and satisfies users. This concept, known as satisficing, mirrors human behavior, where adequacy often trumps perfection. For learners, it reinforces the idea that AI problem-solving is pragmatic, shaped not only by ideals of optimality, but also by the constraints of time, data, and computation. Robotics provides some of the clearest applications of search and problem-solving. A robot navigating a room must plan routes, avoid obstacles, and adjust to unexpected changes. Search algorithms help it explore possibilities, while problem-solving frameworks enable it to sequence tasks coherently. Beyond navigation, robots use search in manipulation tasks, such as determining the best sequence of movements to grasp objects. These applications highlight the direct connection between abstract algorithms and tangible actions in the physical world. They demonstrate how search and problem-solving serve as the cognitive backbone of intelligent machines, bridging theory with real-world function. Operations research is another domain where AI problem-solving methods shine. Scheduling airline flights, optimizing delivery routes, and managing supply chains all involve complex decisions across vast possibilities. AI brings efficiency to these tasks by applying search, optimization, and heuristic planning. These contributions save money, reduce waste, and improve service, showing how AI problem-solving directly impacts industries and economies. For learners, operations research illustrates that the same principles guiding puzzles and games also apply to critical business functions, reinforcing the universality of AI search techniques. Finally, it is important to recognize that search serves as a foundation for more advanced forms of AI. Many machine learning methods, optimization strategies, and reasoning systems build on the basic principles of search and problem-solving. Understanding how AI explores, evaluates, and decides among alternatives provides a conceptual bridge to later topics, such as reinforcement learning and planning under uncertainty. By mastering search, learners gain insight into the mechanics of decision-making that underpin nearly every aspect of AI. This foundation ensures that future explorations into complex algorithms are grounded in a solid understanding of how machines approach the fundamental act of problem-solving. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.